Modern fifth-generation aerial combat is defined by the competition between sensor superiority and stealth shaping. In this highly contested environment, survival depends on which aircraft can remain completely undetected while seeing the entire battle space first. Stealth aircraft achieve a low radar cross-section using geometric facets to scatter waves and radar absorbent materials, or RAM, to convert electromagnetic energy into heat. However, the physics of RAM dictates that it can only be optimized for narrow frequency bands. A coating designed to absorb a 10 GHz wave in the X-band is often highly inefficient against frequencies outside that specific range. India's indigenous solid-state Uttam AESA radar represents the current peak of electronic sensing, but this technology faces a severe physical bottleneck. Conventional semiconductors like gallium arsenide produce significant heat and phase noise when pushed to higher frequencies. This sterna noise limits the radar's ability to distinguish the faint return of a stealthy target from background electromagnetic clutter. To bypass these semiconductor limits, the DRDO initiated a structural pivot known as DRDO 2.0. This research mandate shifts focus towards microwave photonics, using the properties of light, rather than purely electronic oscillators, to generate and manipulate radar signals. Defeating stealth is a challenge of physics rather than raw power. Success requires a fundamental change in how the radar signal is generated to ensure it can operate across a spectrum that RAM was never designed to hide from. The core mechanism for this generation is optical heterodyning. Instead of a traditional quartz oscillator, the system combines two highly stabilized lasers with slightly different optical frequencies. When these two lasers are directed onto a high-speed photodetector, the nonlinear conversion process produces an electrical current that oscillates at the precise difference between the two optical frequencies. This beat frequency allows the system to generate highly stable radio signals, ranging from standard radar bands up to 100 GHz and beyond. This ultra-wideband capability directly exploits the limitations of stealth coatings. While an adversary's RAM may absorb the standard X-band pulses, it cannot simultaneously stop the millimeter wave or sub-terahertz signals produced by the photonic suite. This failure results in a multispectral radar return that exposes the aircraft's position. By modulating the lasers, the photonic radar changes its operating frequencies far faster than adversarial electronic warfare systems can analyze them. This speed, combined with the low phase noise of light-based signals, makes the system virtually immune to conventional radio frequency jamming techniques. Optical heterodyning turns an aircraft's reliance on specific narrow-band absorbent materials into a multispectral vulnerability. Identifying these targets requires an exceptionally high signal-to-noise ratio. Photonic systems possess an inherent physical immunity to the thermal noise produced by electronic components. In DRDO tests, this light-based approach demonstrated a tenfold reduction in system noise compared to existing top-tier electronics. Beyond noise reduction, the system provides a massive increase in bandwidth. While conventional AESA radars typically operate with a 1 to 3 GHz bandwidth, the DRDO's photonic system produces signals at 11 GHz. In radar engineering, bandwidth is directly proportional to spatial resolution. An 11 GHz bandwidth yields a resolution of 1.3 centimeters. At this level of detail, the radar is no longer just detecting a target. It is creating a high-resolution 3D map capable of identifying specific aircraft by their rivet lines or engine exhaust geometries. However, steering such a wideband signal electronically creates beam squint. Because traditional phase shifters use a constant phase shift rather than a constant time delay, the different frequencies within a wideband signal steer in slightly different directions, causing the radar pulse to lose focus. The DRDO solution is Optical True Time Delay. By routing light through microscopic fiber optic pathways of varying lengths, the system physically delays the signal. This ensures all frequencies within the wideband pulse arrive at the antenna elements at the exact same moment, creating a perfectly steered, squint-free beam. To make this technology viable for fighter aircraft, academic centers like IIT Madras are miniaturizing these delay lines and modulators onto photonic integrated circuits. These are microscopic silicon chips designed to handle the high-speed optical processing previously only possible in large laboratory setups. The combination of 11 GHz bandwidth and optical beamforming provides the data needed to map and classify a target's exact structural identity in real time. Moving from electronics to photonics changes the physical architecture of the AMCA Mark II. The transition replaces heavy, vulnerable copper wiring with a more efficient data distribution method. By using lightweight, flexible fiber optic cables, the aircraft eliminates the signal attenuation and electromagnetic interference common in coaxial copper systems. This significantly reduces the overall weight of the aircraft's internal cabling. This weight reduction enables a smart skin architecture. Instead of a single radar in the nose, transmit and receive modules can be embedded across the leading edges of the wings and the fuselage. This distributed sensor web provides the pilot with seamless 360-degree situational awareness. For the conceptual 6th-generation Garrettman fighter, this integration faces extreme thermal challenges. At Mach II plus supercruise, aerodynamic friction generates intense skin heating. Because photonic components are temperature-sensitive, the aircraft requires advanced liquid cooling systems to maintain the stability of the lasers. Integrating photonics embeds the radar's generation and processing directly into the aircraft's frame, turning the outer hull into an interconnected, unjammable nervous system. The development of this technology positions India as the 4th nation globally to field operationally mature photonic radar, a milestone that reinforces its national deterrent posture. This approach differs from China's reliance on VHF and UHF early warning radars. While those systems can detect the general presence of a stealth aircraft, they lack the precision to provide the firing level lock required to guide a missile to the target. In the United States, parallel research is accelerating through DARPA's GRYPY program. Projects led by BAE Systems are focused on combining extreme frequency agility with low noise to maintain air superiority in contested environments. Mastering the generation and preservation of stable optical states is a prerequisite for the next stage of DRDO's sensor research, quantum radar. Using the same lasers and fiber optics developed for the AMCA, researchers at IIT Delhi have already demonstrated secure communication through quantum entanglement over free space links. In a quantum radar architecture, entangled photon pairs are split, with one broadcast toward the target. Because the photons are intrinsically linked, any attempt by a stealth coating to absorb the signal or an enemy system to jam it fundamentally alters the quantum state. This provides the receiver with immediate notification of the target's true location. By moving beyond standard electronics into microwave photonics and quantum entanglement, India is engineering combat platforms with a sensor suite that remains indifferent to the illusion of stealth.